My name is Rajesh Nishtala. So today I'll be talking about how we scaled Memcache at Facebook. Just a little quick intro for this. This was a lot of work with a lot of other people, not just me, obviously. And I can't get through the full breadth of the system in this talk, nor could we actually get through it in the full breadth of even the paper. So if you want to really get into the nitty-gritties, please see us after the talk. So to start off with, what kind of infrastructure requirements do we have at Facebook? I mean, for any system at Facebook, these are the kind of common themes that we tend to see. One is that we tend to need near real-time communication. So when you send a message, we need to be able to see the message. We need to aggregate content on the fly from multiple disparate sources. Take a look at your newsfeed. We need to be able to share and access and update very popular content, like President Obama's status updates. And we need to be able to scale to process millions of user requests per second. So what kind of design requirements does this impose on our system? First of all, we need to support a very heavy read load. I'm talking about over 1 billion gets a second, and we store trillions of items in our cache. We need to be geographically distributed, so we have data centers around the world. We need to support a constantly evolving product. Our product engineers love to hack, and they love to change things, and we need to be able to support these. And we need to be able to support rapid deployment of new features. Luckily for us, we do not handle persistence. We do not make persistence guarantees. We are a cache. We can evict things at different times, and we have mechanisms to support refill of our system. So our basic building block for a distributed key value store is based on Memcached, which you've heard a lot about, so I don't need to go into it. It's just a network attached in-memory hash table. A lot of the concepts here actually apply to any kind of piece that you put in there that applies, but we use Memcached. So a lot of that, it's not limited, the concepts aren't limited to Memcached itself. So what is the rest of the talk going to look like? So let's start off with what a typical thing looks like. We have some web servers and we have some databases. So the first part of the talk, we'll add a few Memcache servers and call it a front-end cluster. The problems here are read-heavy workload, wide fan-out, handling failures. Then we'll scale to multiple front-end clusters. So how do we control data replication and data consistency become the interesting point. And then we talk about multiple geographic regions. And again, data consistency is the name of the game there. So before Memcache, we had a bunch of web servers and a bunch of databases. And the data was sharded across these databases based on your user ID. And just a few databases were enough to support the load, so we were fine. So this was great. So why did we even need to support something like Memcached? So now this gargantuan-looking thing is actually the data dependency graph, a data dependency DAG for a small user request. This is not one of your major user requests. This is a small user request. Each one of these points represents a unit of data fetch and compute that you need to do to be able to render the page. And as you can see, even in this small thing, there's 20 rounds of data fetching that need to happen at best, and all the data dependencies. And so you can quickly start imagining the volume of data that we need to fetch and how a database alone is not sufficient to handle the problem. So let's start with a few Memcache servers. Now we're talking about tens of servers, and our scale here is about millions of operations per second. So we need a lot of read capacity. So we have 2 orders of magnitude more reads than writes. So let's deploy a few Memcache servers to help us out. So what we do is we use Memcache as a demand-filled look-aside cache. That means that if you try to get the key, which contains 0 for value, if it exists, great. If it misses, you ask the database, and then you refill the cache. By being a demand-filled look-aside cache, notice that the cache data is actually being set for the next person to come along and read that data. You already have the data from the database. For updates, the web server will write directly to the database and then invalidate all the data in the caches through a delete. Why do we prefer deletes over directly updating the value? Deletes are idempotent, meaning that we can constantly replay them in case one gets lost or gets delayed through the system. A delete is a delete. It has the same operations regardless. So deletes are pretty good. And it also supports our demand-filled model pretty well. And it's up to the web application to specify which keys we need to invalidate. Now, one of the problems with a look-aside caching is stale sets. So let's just take an example with 2 web servers and a database and some caching again. So a web server reads a value A out of the database and stores it in its local memory. The database gets updated to B by another client externally. Another web server reads the value B. And then the web server B that has the value B is able to set that in because it's on top of its thing and is able to go forward. Now the straggler A comes in and tries to set the value. Suddenly memcache and the database are inconsistent. And this is not a transient inconsistency. This is a permanent inconsistency until the value is deleted out of the cache. This is bad. So what we did was we extended the memcache protocol with what we call leases. With every miss in the cache, we attach a 64-bit lease ID, and the lease ID is invalidated at the server after a delete. So on a set path, we look at the lease ID and check, has the value changed? If not, then allow the set. Otherwise, we throw the set away. This is very similar to how load-linked conditional store operates for those of you who are familiar with processor architectures. The other interesting problem that happens with look-aside caching is what we call thundering herds. So you have a bunch of web servers. They're all accessing a very popular piece of shared content. So let's say some popular celebrity has posted something. These web servers, the value in the database is updated. And then once the value in the database is updated, all the servers see that the value doesn't exist in the cache, and they all simultaneously access the database. With sufficient web servers, that database literally just is unable to keep up with the load and goes down. And this is a very bad experience because that means that anybody that has data on that database, including your user information, cannot use the site. And that is not something that we want to do. So again, we made an extension to leases, which makes the memcache servers arbitrate access to the databases. So essentially, the caches say, I don't have the data, but I know a lot of other people have just asked for the data, so why don't you hold off while somebody else is actually going to refill it for you. So we use the caches to arbitrate access to the database. So great. Now let's move on to our next step of scaling. So now we're going to be talking about hundreds of servers and tens of millions of operations per second. So we have, as you can see, we have more web servers and we need more read capacity. So let's add some more memcache servers. Our items in our cache are distributed through consistent hashing, meaning that all the items, you take the consistent hash of a key and you find the appropriate server that the key resides on. Individual items are rarely accessed, so over-replication of the data doesn't really make sense. Now, if all the web servers are doing this, notice that we have a pretty big problem with all-to-all communication. That means within a very short period of time, all web servers will access all cache servers simultaneously, and this puts an enormous strain on our network and our network infrastructure that we have to handle. One of these problems, it's not all of these problems, but one of these problems is what we call in-cache congestion, or is termed as in-cache congestion, sorry. We issue a wide parallel fetch to many servers. Memcached thinks for a couple of microseconds and returns the value. When all the values come back to the web server, they overwhelm shared networking resources at the client side, not at the server side, at the client side, and you start to see packet drops. So what do? We have a pretty simple sliding window protocol that limits the number of outstanding messages. Larger windows cause more congestion, and smaller windows result in more round trips to the network. So there is a sweet spot, and I encourage you to read our paper about it. Okay, so let's move on. So now let's move on to multiple clusters. Now we're talking about thousands of servers and hundreds of millions of operations per second in the hundreds of millions of operations per second. So here's a view of our front-end cluster, kind of simplified and condensed down. Notice that the all-to-all that I mentioned a couple of slides ago limits our scalability. So if you just naively just keep adding web servers and cache servers, the all-to-all problem only gets worse and worse as you go along. So we need to find a way to actually add in a second cluster. So now a cluster is just a collection of web servers and a cache cluster together. So we have to have 2 copies of our installation. So now comes the problem of how do we keep these caches consistent? And how do we manage the over-replication of data? So now the over-replication of data is a very interesting thing. I don't have time to go through it in this talk, but I highly encourage you to read the paper about more results about it. So what do? We use, our database storage servers are MySQL. So what we have is a system called McSQL that essentially looks at all the database transactions that have been committed, reads those out of the commit log, extracts the Memcache items that need to be invalidated, and then this program just broadcasts the invalidations to all front-end clusters. Now, this system has a very nice property that the cache data must be invalidated after the database operation commits. Otherwise, you have a risk of you risk seeing stale data. So by using the databases to invalidate the cache, you guarantee that the cache and the data, that upon a cache miss, you can actually see a fresh value of the data. Now, you might be wondering, these front-end clusters, these are pretty hefty things, and you were talking about a lot of packets flowing around the system. And you're actually quite right. There's a lot of packets, and doing it naively causes too many packets in the system. So we need to fix that problem. So let's say that we have a few database instances with McSQL running on top of them. We then take these database instances and then route them to what we call a layer of Memcache routers, or McRouter. These then fan the deletes out into different front-end clusters. Each front-end cluster has its own set of McRouters that are running, and then they, in turn, broadcast them out. One of the significant advantages of doing this is that the inter-cluster bandwidth is much smaller than the intra-cluster bandwidth. Right? So by doing this, we try to minimize the amount of bandwidth that we use and maximize our packet density. And we can see that we get about an 18x reduction in the packet density. This also, by the way, makes configuration management a lot easier. You don't have to worry about where all the Memcache servers are. You just need to worry about what all the Memcache servers are downstream from you. And each stage can buffer its deletes in case of failure of a downstream component. Now, let's move on to a little larger of a scale. Now we're talking about thousands of servers geographically distributed around the site, and now we hit our magic number of over 1 billion operations a second. Facebook employs geographically distributed data centers. The primary motivation for this is fault tolerance, because we don't want an earthquake or hurricane to affect us. Facebook needs to stay up so that people can communicate. So we distribute our data centers around the world. Here I'm showing our example of our data centers in Forest City, North Carolina, Prineville, Oregon, and Luleå, Sweden. So one of the things that happens with geographically distributed databases, and again, going back to one important thing I forgot to mention in the slide, is that we have a single master. There's a single set of master databases, and the other regions have a replica of the database. So how do we handle writes to our system in non-master regions? So a web server will actually just directly write to the master database. We'll make the cross-country connection and just write directly to it. The reason that we are okay with this, again, going back to that, is that we see 2 orders of magnitude more reads than writes. So we are a read-dominant system, not write-dominated. So we write to the master, and we delete from the local memcache. Great. So far we haven't had to make any changes. But as we've seen, we use MySQL replication to take the data from the master database over to the replica. But there's a race here. So if another web server tries to read the data, you don't know which value of the data that you have. Do you have the latest value or do you have an old value? So thus we could be setting potentially stale value back into the cache, again, resulting in a permanent inconsistency, which is a very bad thing. So what we do is we employ a set of what we call remote markers. And these are essentially a special set of flags that indicate whether a race is likely. So first, we set a remote marker in our memcache that say, hey, we're about to do a cross-country write. We go ahead and do the cross-country write or cross-Atlantic write. We delete the value from the cache. And then the MySQL replication comes in to the cache, and then MySQL replication will delete the marker. On the read path, which is probably the more interesting path, if the marker is present, that means that the replication hasn't finished. We'll read the data directly from the master. Otherwise, we'll read it from the local replica. Now, you might all still, again, be wondering why we are able to do this. And again, misses are rare, right? We try to keep a good amount of the data in the cache. So we are, again, very read-dominant a system. So circling back and putting it all together, we first started off with a few web servers and some databases. We then added a front-end cluster. Now here, the problem was, how do we deal with a read-heavy workload? How do we do wide fan-out? And how do we handle failures in the system? Then we scaled out to multiple front-end clusters. Controlling data replication and data consistency was an interesting problem here. And then finally, we moved on to multiple regions. So through our system, we've learned many different lessons, including while building the system. One of them was we like to push complexity into the client whenever possible. So if you notice, all our work, the bulk of it is in the client. There is no server-to-server communication in our system. And we think that really helps our operational ability and our ability to scale the system out. Second, operational efficiency is as important as performance. So we go through great lengths to improve our operational efficiency of the stack. One of the examples that we've seen here is the multiple levels of routing that we do for an invalidation pipeline and how it simplifies our configuration management. Performance-wise, it's a lot slower to go through multiple steps, but operationally, having to keep the configurations tight and local makes it much easier to deal with the system. And finally, separating the cache and the persistent store allows them to be scaled independently of each other. So our caches handle our read rate, our databases handle the update and storage capacity. So with that, I'd like to finish and take any questions that you guys might have. Thank you very much.
Hi, Anirudh Bala, Microsoft Research. I noticed that in the talk you never mentioned about bottlenecks of a single Memcache server. Is that because you didn't have bottlenecks within a single server?
So the reason that I haven't mentioned bottlenecks within a single server is that it is an important problem. And actually, if I refer you back to the all-to-all problem that we have of all Memcache servers talking to all web servers, if you have to talk to all Memcache servers within a span of a very short period of time, the tail of that distribution, even if the average tends to be fine, the tail of that distribution tends to get very hot and almost white hot. So if we want to provision our Memcache servers, we have to not only provision for the average case, but the worst case scenario. And that's where the throughput really starts to make a difference. So we have to kind of provision our machines in that regard.
Okay, I have just one more question.
Yes.
I know that you use some SSDs and flash on the database side, but have you thought about using flash and SSDs on the Memcache side?
Yeah, so we actually have a recent blog post about a Memcache flash-based storage that presents a Memcache interface. We use Memcache and flash for different types of data. So like all data is not created equally. So for the colder data set, we look at flash as an interesting option for us as well in the cache.
Thank you.
Yeah.
Cool. Dave Anderson, Carnegie Mellon. First of all, I've got an implementation of Memcache to sell you. We should talk. So my real question is, some of the uses that I'm going to say you, and I mean Facebook here, seems to use Memcache for are due to legacy decision-making in the evolution of a very complex big system.
Okay.
Is that a fair statement before I continue?
So I will say that I used to think so, but I don't think so anymore.
Okay,
right?
Good.
Is that some of the problems of high fan out and high just a sheer volume of communication that we have dictate that we need a very fast, scalable in-memory key value store, right? Whether that's implemented with Memcached itself, whether that's implemented with your favorite legacy other system, that's up to you. But having a very fast and efficient in-memory key value store to be able to serve the needs of the site is critical. And I think having Memcache plays that role really well. And Memcached as a server is a technology that was fine, and there was absolutely no reason to replace it. So we've been going with it, and it's been working great.
Okay. I think you actually answered my question, which was going to be, if I made you president of the world, where would you still use Memcached? And you could change anything about the system architecture underneath. Like, where do you think the fundamental requirements are for something like Memcache? And I think you said the high fan out.
Yeah, and I think it really is the ability to fetch a lot of data items very quickly. As one of my friends, Domas at Facebook, likes to say, we have a small data problem, not a big data problem, which means that we need to be able to fetch a lot of small items very fast and do a lot of them. In the time that we're talking about like a few billion operations, a few billion gets have happened in just the past couple of seconds that we're talking about, right? So we need to be able to handle this kind of rates, and using a system like Memcache helps with that tremendously.
Cool. Thank you.
Hi, Amar from Microsoft Research. So my question was regarding the size of your cache and the average utilization of items in the cache. Could you tell us a little bit about that? Do items just hang around in the cache for a long time without being used?
So one of the things that we talk about in our paper is what we call pools. So essentially how we partition our data sets. So different pools have different characteristics. So there's these things called high churn workloads in which like data is turning over a lot. And in the high churn workloads, you'll tend to see that items live for a couple of days, maybe a few hours, depending on how the tier is sized. And then you'll have some other data which we really would like to stick around in the cache because the cost of a miss is very high. So for those, we keep it around for a little bit longer than that. But one of the important things about scaling and separating our persistent storage from our caching layer is that our caches are not responsible for storing the long tail of data that we have on the databases. Our databases have a lot of stuff on them, right? But the caches don't need to store all of that. They just need to store the hot head, which is effective for us.
So if I get you right, you're saying most of the items are in the cache are used a lot.
Yeah. It's not that most of them, it depends on the virality of the content. For example, if I were to post a photo, I guarantee you it's not, like a lot of people aren't going to see it. Whereas if somebody else was going to post a piece of viral content, then the other people the content is likely to increase in virality. So it really depends on the items itself. So I can't say a priori.
Thanks.
Hi, I'm Marcus Aguilera, Microsoft Research, Silicon Valley. Just a clarification in the lessons that you learned. You mentioned that you'd like to push the complexity as much as possible to the clients.
Yes.
And by that, just clarification, you mean to the client-side library, or you mean the actual client which is using the library?
So this is actually the client-side library.
Got it.
So we have, so what we have is that Memcache router that I mentioned. I didn't get a chance to go into it in the talk, but we have that residing on every one of our web servers, and that is really where the guts of the distributed system actually lie.
Yeah, that makes a lot of sense. Thanks.